Great. Thank you, Jay, for the gentle ribbing about my profile. The bio was largely taken from an internal University of Minnesota site meant to introduce me to graduate students and the like. So I mentioned I like growing flowers and vegetables and things like that, which I do. Not embarrassed to say. Walks in the park, things like that. What I want to talk to you about today is largely life cycle assessment. I want to talk to you about its uses and its misuses. It's come up a lot today. I've had an opportunity in recent years to become more familiar with the ways in which it's structured for analyzing questions such as, is one thing better than something else? And that can be interpreted in many different ways. I'd also like to talk about some of the uncertainties associated with future biofuel production here in the US, and then finish with some methods that we're developing to advance life cycle assessment as use for policy. Impacts. Here's a slide that summarizes EPA's Triennial report to Congress, which it is required to do as part of the Renewable Fuel Standard. Biofuels could be good. They could be okay. They could be bad. It all depends. This phrase, "it all depends," matters tremendously and comes up time and time again. Largely the conclusion of the NRC report on biofuels that was released in 2011 as well. One can see from the slide that depending on many different factors that go into the production and use of biofuels, the impacts on things such as soil quality, air quality, biodiversity, invasiveness can be quite varied, and that depends on feedstock. It depends on where biomass is grown, how it's converted. What about greenhouse gas emissions, you say? Well, similar variation exists for what different researchers have found in life cycle emissions related to biofuels. Here is a summary table from that NRC report that shows life cycle greenhouse gas emissions here in grams of carbon dioxide equivalent per megajoule for corn ethanol. And as a reference, gasoline is probably somewhere around 95 or so life cycle greenhouse gas emissions. So you can see that some investigators have found that corn ethanol is worse for greenhouse gas emissions, and others have found it's better. And a lot of that is in the underlying assumptions in the study. Now, this is somewhat surprising because life cycle assessment is standardized. There's an ISO standard, the 14040 series. However, the standard itself is more directed at the reporting and consistency in terminology in life cycle assessment than it is in the particular steps that one takes when conducting LCAs. And that is actually an excellent first step and reflects the diversity in ways in which life cycle assessment is used for product development improvements, strategic planning, public policy making, marketing, etc. So I want to tell you a story of 3 LCA studies. This is actually a summary of a discussion in that NRC report that looks at how 3 different individuals may use LCA. We'll look at this from the point of view of an ethanol plant owner, an ethanol industry analyst, and say somebody involved in regulation. So each of these individuals may construct an LCA considering different volumes of ethanol. The ethanol plant owner may be wondering about the greenhouse gas profile, for instance, of fuel being produced in his or her facility. Ethanol industry analyst may be wondering about average corn ethanols produced in the United States in a given year. Regulator may be interested in the marginal increase in ethanol production that occurs as a result of a policy, say RFS2. Each would choose different data as model inputs. One might choose, for instance, the yield of corn. The first ethanol plant owner may choose the yield of corn that is grown and harvested directly in the supply chain, feeding into that facility. Ethanol industry analyst may choose average U.S. corn production. Government regulator may choose the increase in yield that's expected as a result of a certain policy. All of those methods are correct, but they need to be used only for their intended purpose. Otherwise, you run into trouble. There are many different flavors of LCA. There's attributional LCA. That takes the world and looks at the sum of human impact and divides that among all the different things that we produce and do. That's attributional LCA. What are the total emissions from the process and material flows used directly in the life cycle of a product? Okay, so this is supply chain. And then there's consequential LCA. That looks at how the sum of human impact changes as a result of decisions to produce or not to produce different things. So what is the change in total emissions as a result of a marginal change in production and consumption of a product? And these can lead to different results. The bottom, consequential LCA, looks at market-mediated effects that may occur as a result of changes in supply and demand of different products. Here's an example of how intentions may have been good for how to use LCA, but the application failed miserably. This is EPA's RFS 2's final rule of comparison of corn ethanol to gasoline. The summary finding was that corn ethanol reduces greenhouse gas emissions 21% relative to gasoline. Now, corn ethanol had to hit a 20% reduction in order to qualify. Of course, most of it was grandfathered in, so it's basically an academic question. But how did these results, how were they actually interpreted? Well, if you look at EPA's assessment, the way they got to 21% was to take the 2022 estimated values, there, 17%, 27%, et cetera, do a weighted average for how they believed the industry would look at that time, and then that happened to be 21%. But if you look at any of the other years, 2012, 2017, corn ethanol as it's produced in 2012, last year, according to their assumptions from 2008, 2009, was 33% worse in greenhouse gas emissions than gasoline. So this is an application of LCA that essentially went awry, and whereas most of the production over the course of the Renewable Fuel Standard occurs during the years 2008 to 2022, the industry is judged solely at that end point, once most of the land use change has already been essentially accounted for in the system. So a bit of slick accounting. Energy independent, you've seen this slide before. Oh, how many times today already? The volumes, it all looks very straightforward as to the amount of fuels that will be produced. Well, corn ethanol, certainly we're almost there. Other advanced biofuels can come online, sugarcane ethanol, et cetera. And the cellulosic biofuels, which for a number of reasons that have been discussed today, probably will not be met. But if we were to meet these, and this is where a number of groups have made that assumption of if we were to meet these, what types of biomass would we grow and how would it be grown? And this is a slide summarizing DOE's update to the billion-ton study, EPA's RFS 2 final rule assumptions, and then USDA's roadmap for what biomass will be produced to satisfy the Renewable Fuel Standard. As you can see, all of them largely agree that corn ethanol will be produced at 15 billion gallons. But beyond that, things get varied, and they vary very quickly. Perennial grass ethanol is highly relied upon by EPA, whereas USDA, for instance, highly relies upon annual energy crop ethanol, sweet sorghum, and other sources. EPA relies highly upon municipal solid waste biofuels and imported biofuels, whereas those are almost non-existent in USDA's and DOE's interpretations. So large differences, even among agencies, in how the industry is projected to develop. And this affects many things. It affects where, for instance, DOE funds pilot and commercialization facilities, where USDA invests dollars in its research programs, how EPA institutes its final rule for different biofuels. Also great differences in projections of where biomass will be grown. You can see here for corn stover, for instance, according to USDA's projections, Minnesota, for instance, is a large producer of corn stover. In EPA's estimates for final rule, Minnesota has none. So if you're looking to invest any sort of resources into the development of the industry, you have very different potential outcomes depending on which of these projections you are listening to. Look at perennial grasses. In USDA's scenario, CRP land is open to production, and that makes a huge difference, whereas DOE relies almost exclusively upon Kansas, Oklahoma, and Texas for production of switchgrass in 2022. USDA has that shifted north, and that, of course, will affect the change in ecosystem services and the change in water quality, depending on how and where that switchgrass is grown. So when we look at assessing the environmental impacts of biofuels, typically there have been two types of studies. There have been these LCA studies, these life cycle assessment. They typically tell us a little about where resources are used and where emissions occur, though, let alone where the impacts occur. So they're very broad. They use these broad characterization factors, and that's a problem. There's not much specificity in the impact stages. There are also landscape level studies. You've seen some of those in prior talks. But those miss the impact that happens beyond a particular landscape. It misses impacts that may occur in the supply chain or as a result of market-mediated effects. And this is a big problem because each one has major deficiencies. And so what I want to do is to describe some work that we're doing that integrates the best part of both of these types of analyses in coming up with spatially and temporally explicit life cycle inventories and impact analyses. I'm going to focus on air quality in this. This is a paper published last fall in Environmental Science and Technology. Christopher Tessum, a grad student working with us, Julian Marshall in civil engineering at Alta University of Minnesota here. So life cycle assessment, we have a number of stages of production and use. We sum up the resources used and emissions released in the stages of ethanol and compare that to those in gasoline, typical attributional style LCA, and you see which is greater than the other, and that's how you make your choice. Now, of course, there are all sorts of problems with simply using that approach, but what I want to do now is focus on how we can improve that. So these are results from the GREET model from Argonne National Lab. This is nothing we did. This is just straight model results. If you run their baseline scenarios, looking at emissions of VOCs, SOx, NOx, and ammonia. Actually, the ammonia numbers are ours. We adapted GREET and the GREET platform to handle ammonia. And you can see here emissions both in production and use of fuels for average U.S. gasoline, corn ethanol, cellulosic ethanol from corn stover, and cellulosic ethanol from switchgrass. Now, one thing you'll notice in almost each of these cases is that tailpipe emissions in vehicle use are pretty equivalent. There's very little difference in VOCs, SOx, NOx, and ammonia for total emissions. Now, there may be differences in VOCs and speciation of those, but in terms of total quantity, there's very little difference. For VOCs, because the use phase dominates the life cycle, you do pretty well by capturing emissions in that phase. But when you start looking at SOx, NOx, and ammonia, if you're just looking at tailpipe emissions, you're missing most of the story of the impact of those different fuels. So it really speaks to the importance of looking at the life cycle inventories when developing impact assessments. So certainly it's important to understand the tailpipe emissions, but you need to know a lot more. This is just more detailed GREET model output for what we saw before for a few more species, showing the different stages and the major stages in the emissions of the different fuels. I'm not expecting you to memorize this, but just to show you the complexity of the different stages. In reality, the stages you see here are really aggregations of what may actually hundreds of different emission sources in the supply chain of production and use of these different fuels for each fuel. So what we did is we went through the model and we took that we took the sort of geographically agnostic results that and temporally agnostic results that are reported in GREET, simply just reported by stage, and develop profiles for each of those. So we use data sources from a number of different available publications to help us understand the different sectors that contribute to the production and use of the different fuels. There's just a listing of some of those to give you some confidence that we did our homework. We tracked a number of different pollutants in this. So as I mentioned, VOCs actually, there's a conglomeration, aggregation of many different potential species. We had to account for the fact in our modeling domain of North America, some of the emissions in the supply chain are international from trade. We subtract those out. And what we get are individual processes, hundreds of these. So as an individual process, these are 3 processes. So for each process, here vehicle tailpipe emissions, ethanol plant evaporation, non-combustion, coal mining, cleaning, and non-combustion. We have spatial emission profiles, and for here 3 different fuels for each of the species that I showed in the previous slides. So you can imagine there are lots of these that describe the emissions associated with each of the different steps. So there's just 6 of them, all in all, that you can see. You can see also their temporal profiles, for instance, fertilizer nitrification there, looking at the monthly profile and the daily profile as well. Vehicle tailpipe emissions at the bottom left shows the 2 peaks corresponding to the morning and evening rush hours. So you take all those individual profiles and you layer them, one on top of the other. Hundreds of those layered on top of the other for each species, for each fuel. And what do you get? You get a nice spatially explicit, temporally explicit inventory of fuels. These are done at hourly time steps over the whole year as well. So you can imagine these are quite large databases, terabyte size. These are some cumulative inventories. Here's one for VOCs. You can see that since VOCs are largely dominated by tailpipe emissions, the large emissions in the Northeast, but looking at corn ethanol and Stover cellulosic ethanol, you see the increased emissions in production in the Midwest as a result of increased fuel production. Here looking at ammonia for gasoline compared to corn ethanol and Stover cellulosic ethanol. Again, ammonia emissions much higher in the Midwest due to production. Primary PM 2.5, some interesting things going on here, not the least of which is in the Stover cellulosic ethanol case. You have high emissions in the Midwest, and you actually have negative emissions in some other areas due to the fact that cellulosic ethanol co-generates electricity, which then is sold back to the grid that offsets fossil production. So that's some of the blue areas you see there in Powder River Basin and in Appalachia. As I mentioned, we have these cumulative temporal emission profiles as well, done on hour time steps throughout the year. So that's everything in that paper that I described so far, that gives these profiles and describes where emissions occur. Now, where emissions occur is not enough, and I'm going to just talk briefly about other work that we're doing that's in progress and review right now, that on the next steps, where you take this. So we're looking at advanced dispersion modeling, air quality impacts, and then finally environmental justice. So going from emissions, concentration, exposure, intake, dose, and finally health effects. So I'm going to show you some modeled volumes here. The essentially marginal increase in ethanol produced as a result of RFS2. So it was estimated that because of RFS1, we would essentially get to about 7.5 billion gallons of ethanol. RFS2 brought us up another 7.5 billion gallons to 15 billion gallons. And then we took as a realistic increase, if you will, of 5 billion gallons per year of Stover cellulosic ethanol. Stover cellulosic ethanol likely being the lowest cost feedstock available. So our scenarios that we ran are 5 billion gallons a year of Stover cellulosic ethanol, 7.5 billion gallons a year of corn ethanol, and the sum of those two. And then in the coming slides, I'll compare those to the energy equivalent volumes of gasoline that could have been used in their stead. So here's what we have. Starting from the left, 5 billion gallons of Stover ethanol, and then 7.5 billion gallons of corn ethanol, and then the combined case. On the bottom, the comparable amounts of gasoline on an energy equivalent basis. So certainly the Midwest gets socked quite bad from the increased emissions in production of these fuels. Here's the distribution of health impacts. This is in the morbid metric of deaths per year in each of the grid cells. And then from this, we can look at the predicted deaths per year as a result, and then assign an externality damage cost here per gallon of ethanol, anywhere between $5 and $8, at a value of statistical life of $9.1 million, compared to gasoline at 76 cents per gallon. Look at the demographics of the populations hit by these changes, and this is where things start to get interesting. Looking at white, non-white populations, low-income, high-income populations in rural and urban. We can see here if the number is greater than 1 in the first column, it's non-white populations getting hit more. So both scenarios, ethanol and gasoline, non-white populations are being impacted more by this marginal increase, but non-white populations are being impacted even more than in gasoline scenarios versus cellulosic stover ethanol. Low income, high income. Again, low income is being hurt more in the gasoline cases, in both cases, but it's a slightly lower total impact. And then rural populations, urban populations are being damaged more in all cases, but in the case of ethanol, rural populations are being impacted more. Okay, so a lot going on in this slide. Actually, I think I will end there, but a lot going on. Happy to answer any questions you have, unless you want me to wait for the second one.
Maybe we'll do the second lecture and then move on to questions.
Sounds good.